In 4.2, we're going to continue on with properties of polynomials, but the main focus of this section is going to be to find the zeros, or in other words, the x-intercepts of our polynomial. The first thing I'd like to talk about has to do with our idea of polynomials being continuous. If you look at this graph here, and sorry, it should go all the way up, all the way down. We're going to talk about what we call the intermediate value theorem, and I'm just going to say IVT for intermediate value theorem. The intermediate value theorem, or IVT, depends on a continuous smooth function like polynomials. So let's say you do have a polynomial, and let's say that for real numbers a and b, the corresponding y values, p of a and p of b, have opposite signs. Let's go ahead and look at this graph. So here we have an a value, and it's going to correspond to some point here that would be a p of a, so some y value. And then given this b value, it will correspond to some point p of b. So now let's say that P of A and P of B have opposite signs. As in this diagram, notice that P of A is above the x-axis, so it's positive or greater than 0. P of B is below the x-axis, so it's less than 0 or negative. So they have opposite signs. One is positive and one is negative. Because they have opposite signs and because polynomials are continuous, that guarantees that there's going to be at least one real zero between A and B. In my diagram, I actually have 2, 3. So I actually have 3 zeros between A and B. However, IVT just guarantees that you have at least one. There could be more than one, but there's at least one. And that's going to be our focus, is to be able to find the zeros of our polynomial. In example 1, it says show that a polynomial function, in this case our function is p of x equal to 3x to the third plus 7x squared minus 5, has a real zero between -1 and 1. Notice it doesn't say find the zero, it just says show that it has a zero. So what that means is we're supposed to use IVT. I underlined show because oftentimes when you see show, demonstrate, determine, prove, those types of words, it means that you have to show a process and come to a conclusion. So you're not just solving something. So if we were to use IVT, the first thing we want to do is figure out what P of -1 and P of 1 are equal to. Because if they happen to be opposite in sign, then we can use the theorem to conclude that there exists a zero between -1 and 1. If I were to put -1 into this polynomial, it would be equal to 3 times -1 to the third plus 7 times -1 squared minus 5, which would be -3 plus 7 minus 5. So it looks like it's going to be -1. So notice that P of -1 is negative. P of 1 is going to be 3 plus 7 minus 5, which would give me a positive 5. So I've shown that P of -1 is negative and P of 1 is positive. So now what does that mean? That's not enough. It says show that this function has a real zero. All we've shown is that P of -1 is negative and P of +1 is positive. However, since they do have different sides, signs, we can conclude by the intermediate value theorem, or IVT, that there exists at least one zero between -1 and 1. So it's not enough that you just show that 1 is negative, 1 positive. You have to say, okay, well, so what? Why does that show that there's a 0? And the reason is that conclusion that by IVT, there does exist at least 1 0. So this is actually a proof, which is what we do a lot of in Math 140 and also in calculus. So moving beyond the IVT, we're going to expand more on the zeros, and we're going to work our way to finding the zeros of a polynomial. The first step is this special case where we are going to be dividing by a binomial of the form x minus k. So x minus some number. In example 2, it says to divide 3x to the third plus 7x squared minus 5 by x plus 1. So this can be written in that form. It would be x minus a negative 1. So in this case, our k value is going to be -1. So I am dividing by this binomial x plus 1. So at this point, what we need to do is review long division of polynomials. So x plus 1, that's what we're dividing by. That's what we call our divisor. That would go on the outside of our division bar. And then what goes underneath our division bar is 3x to the third plus 7x squared minus 5. However, notice that we're missing an x term. So we have to put in a 0 placeholder so that all of our terms line up. So 3x to the third plus 7x squared, missing my x, so I'm going to put in a plus 0x as a placeholder, minus 5. Now with long division, remember what you do is you ask yourself, what do I need to multiply this x plus 1 by to get the 3x to the third and so on, which is kind of difficult to understand. So instead, what you should be looking at is the leading term. So the leading term in the divisor, x plus 1, is x. And the leading term for the polynomial that's underneath the division bar is 3x to the third. So just look at those, ignore everything else, and say, what do I need to multiply the x by to get 3x to the third? And then that should be 3x squared. So when you multiply the 3x squared by x plus 1, by that whole divisor, you get 3x to the third plus 3x squared. Now you don't have to do this math off to the side, but sometimes it's easier to see. And then what we're going to do with that is we're going to put it underneath the 3x to the third plus 7x squared. So this is just long division where you multiply, subtract, multiply, subtract, multiply, subtract till you can't do it anymore. So the 3x to the third plus 3x squared. And then we subtract down. A little bit awkward because you're going to have to distribute that negative to that second term. So the 3x to the third minus 3x to the third is 0. But then the 7x squared minus a 3x squared, that's going to give you a positive 4x squared. And then we bring down our next term. And we ask ourselves again, what do I need to multiply the x plus 1 on the outside to get a 4x squared? Okay, again, just paying attention to these leading terms. What do I need to multiply x by to get 4x squared? Well, that would be a positive 4x, so we put a plus 4x. And when you multiply the 4x by the x plus 1, you should get 4x squared plus 4x. But if you don't see that, then you would do the multiplication off on the side. 4x times x plus 1 equals 4x squared plus 4x. So that's what goes next, 4x squared plus 4x. And since we're doing long division, we're going to subtract down. So 4x squared minus 4x squared is 0. 0x minus 4x would be a negative 4x. Bring down the last term, the minus 5. Again, what do you need to multiply the x by to get negative 4x? And that would be a minus 4. So the minus 4 times x plus 1 is equal to the negative 4x minus 4. And then you subtract down. Negative 4x minus a negative 4x would be negative 4x plus 4x, that's 0. Negative 5 minus a negative 4 is negative 5 plus 4, which would be a negative 1. And we can't go any further because the negative 1 is too small. The x plus 1 is of a larger degree. So this negative 1 is our remainder, and we're going to use r for remainder. How we write our solution is always the 3x squared plus 4x minus 4, that would be what we call our quotient. And it's always quotient plus remainder over the divisor is x plus 1. So it doesn't matter if the remainder is negative or positive, it's always a plus remainder over divisor. So this 3x squared, so let me just write this out. This 3x squared, that was our quotient, our solution, plus 4x minus 4. And then we were adding it to our remainder over what we were dividing by our divisor, which was x plus 1. This 3x squared plus 4x minus 4, we're going to let that be what we call q of x. It is a polynomial, so that would be our quotient polynomial. So q for quotient, but since it is a polynomial, we'll also call it a polynomial. So it's quotient plus remainder over the divisor x plus 1. So in general, this is what our division will look like. We'll take our polynomial p of x. So let's go back up a little bit. Our p of x is this polynomial that's underneath the fraction bar. Sometimes we call this a dividend when we do division. And this x plus 1 on the outside, sometimes we'll call that the divisor. So this p of x, this polynomial that we started with, if we take this polynomial and we divide it by our binomial x minus k, it's going to be equal to the quotient plus remainder over x minus k. So that's what we just wrote up above. So now the first part of this theorem says that if p of x has degree n, then the quotient polynomial q of x has degree n minus 1. So that's just a little fun fact. Let's double check. So our quotient polynomial, the 3x squared, that has degree 2. And our polynomial p of x, that has degree 3, because it's 3x to the third. So that checks out. Degree of the quotient is 1 less than the degree of the dividend, p of x. That long division was a pain. And it was a pain because of the variables, because of the subtraction, because we had to figure out what we needed to multiply by. So now we're going to try a different method called synthetic division. And in synthetic division, the idea is to get rid of the variables first, and then also change it from subtracting to adding. So with the long division that we did previously, it was multiply, subtract, multiply, subtract, multiply, subtract. With synthetic division, it's going to be multiply, add, multiply, add, multiply, add. And without all those variables, and with the addition, there should be less chance of error. So with synthetic division, again, it has to be of the form x minus k for us to use synthetic division. And we're going to revisit that example 2. Here I wrote example 1. It was example 2. And we're going to do that division again, but we're going to use synthetic division. So the first step would be to remove all the variables. So the 3x to the third plus 7x squared minus 5, if we get rid of the variables, but we still have to write it from the leading coefficient down, and we still need that 0 placeholder. So we're still going to have 3, 7, 0 for that missing x, and negative 5. We're just leaving off the variable x, and that's what's going to go underneath this fraction bar. On the outside, we're going to get rid of the x and the x plus 1, but in order to change it from subtraction to addition, we're going to, instead of using a plus 1, we're going to do a minus 1. So that will change us from subtracting down to adding down. So a minus 1, again, we got rid of the variable x, is going to go on the outside. And now leave a little bit of space and draw your bar. The first thing we want to do is bring down the first term 3. Next thing we want to do is our multiplication. So remember, it's multiply, add, multiply, add. What do you multiply by? Well, you're going to multiply this 3 to the divisor negative 1. 3 times negative 1 is negative 3. That's going to go underneath the next number, which is 7. And then we're going to add. So multiply, put it underneath the next number, and then add. 7 plus negative 3 is a positive 4. What do we do with that 4? Again, we multiply it by the negative 1. So 4 times negative 1 is negative 4. That goes under the next number, which is 0. And then we add. 0 plus negative 4 is negative 4. Now we take that negative 4, multiply it by the negative 1 to get a positive 4, and then we add to get a negative 1. So recall that that negative 1, that was our remainder when we did the long division for example 2. Well, what about the quotient? Well, that would be these numbers here. The 3, the 4, and the negative 4. So if negative 1 is the remainder, then working your way from right to left, the negative 4 is going to be the constant term. The 4 is the 4x. The 3 is the 3x squared. So you keep adding a higher exponent to each x. So this becomes 3, that's the x squared. The positive 4 becomes a plus 4x. The minus 4 is just minus 4, plus remainder over, we were dividing by x plus 1. And that's what we had when we did the long division from example 2. So this is synthetic division. Again, it only really works if you're dividing by a binomial of the form x minus k. Let's try this again in example 4. We're going to use synthetic division to divide x to the third minus 3x squared minus x plus 3 by x minus 3. So again, we're just going to put the coefficients. So remember, there is a 1 in front of the x to the third, and there's a minus 1 in front of the x. So we're going to put in 1, negative 3, negative 1, positive 3. Notice that I have no missing terms, so I don't need a 0 placeholder. And I'm dividing by x minus 3, so you take the opposite of a minus 3 would be a plus 3. Leave a space. Bring down the first term 1. 1 times 3 is 3. Add negative 3 plus positive 3 is 0. 0 times 3 is 0. Add negative 1 plus 0 is negative 1. Negative 1 times 3 is negative 3. Add, you get 0. So the remainder here is 0. And now translating this 1, 0, 1, remember this would be the squared. So that's going to be 1 times x squared, or x squared, plus 0x minus 1, plus remainder is 0, over, we're dividing by x minus 3. However, I don't really need to write the 0x in my final answer. And then the remainder 0 over x minus 3, that's just 0. So that can be simplified as well, which means the final solution to this division is x squared minus 1. We're going to next go into some really nice theorems, but what I wanted to bring your attention to is an example for what we actually did was we took our polynomial p of x, and when we divided our polynomial p of x by x minus 3, we got this solution, which was x squared minus 1. So what that says is that p of x is x minus 3 times x squared minus 1. If you multiply out the x minus 3 and the x squared minus 1, you will get x to the third minus 3x squared minus x plus 3, which is what we're working towards. What we're working towards is breaking these polynomials into smaller and smaller pieces, or factoring it. But before we start delving into that, let's look at some two nice theorems. The first is going to be our remainder theorem. So the remainder theorem says that if you take a polynomial and you divide it by x minus k, then your remainder will be equal to p of k. So again, that's just words. What does that mean? Well, if we go back to our example 3, so recall our p of x in that case was 3x to the third plus 7x squared minus 5. So this is just a really nice trick. Our k, since we're dividing by x plus 1, our k was actually a minus 1. Remember, it's the opposite. And in that particular example, our remainder was negative 1. So by this theorem, it says that p of negative 1, because that's our k value, is going to be equal to the remainder r, which in our case was negative 1. So cute little trick. Let's just verify that by putting in negative 1 into our polynomial to get 3 times negative 1 to the third plus 7 times negative 1 squared minus 5. So that should be negative 3 plus 7 minus 5, which is negative 1. That checks out. By the remainder theorem, we get p of k is equal to the remainder. So p of negative 1 is equal to the remainder negative 1. Let me do this again with example 4. Just double check this. In example 4, our last example, we had our polynomial p of x equal to x to the third minus 3x squared minus x plus 3. And in this case, we were dividing by x minus 3, so k is the opposite. It's a positive 3. And remember, our remainder in this case was 0. So by this theorem, p of 3 should be equal to 0. If I put in 3 into my polynomial, I'll get 3 to the third minus 3 times 3 squared minus 3 plus 3. That would be 27 minus 27 minus 3 plus 3, and that is 0. So it checks out. So fun little theorem. We'll move on to probably the most important theorem, which is our factor theorem. So this is our goal here, is to be able to take our polynomials and to factor them down into smaller and smaller pieces. And we're going to use this factor theorem for that. So let's say that a polynomial has a factor of x minus k. So if it does have a factor of x minus k, then that can only happen if p of k is equal to 0. So remember, this is a 0 of the polynomial. Whenever you put in some value into your function and you get back 0, that k value is the 0, which is our x-intercepts. So the 0 of a function is the x-intercept. Let's go ahead and look at example 4 again. So I had talked about this earlier. Remember that p of x is equal to x to the third minus 3x squared minus x plus 3. And here we were dividing by x minus 3, and we ended up with p of 3 equal to 0 by the remainder theorem. So now by this factor theorem, since p of 3 was 0, right, put in 3, the remainder was 0. That means x minus 3 is a factor of our polynomial, which again, and I had talked about this earlier, means I can take this polynomial and factor it into x minus 3 times something. So remember, whenever we factor, it's always parentheses following, right? So I pull out the x minus 3, that factor. What remains is in parentheses. Well, what remains is that quotient, x squared minus 1. that we got when we did our synthetic division. And now that I've broken this polynomial, it's factored now, it's just not completely factored. I've broken it down further into smaller pieces. I can actually see that the x squared minus 1, that's difference of squares. So I can factor this polynomial even further so that it's x plus 1, x minus 1. And now I've broken up this polynomial into these 3 factors, and these are actually linear factors. Where if you look at each one of these factors, it'll give you the 0 or the x-intercepts of the polynomial. So the x minus 3, if you put in 3 for x, you're going to get 0. 0 times whatever the rest of that is going to give you 0. So 3 is one of our zeros. If you look at the x plus 1 and you put in negative 1 for x, that becomes 0. 0 times all the rest of the stuff is going to be 0. And if you look at the x minus 1 and you put in 1 for x, then that would be your third 0. Okay, so if it's a factor, it gives you the zeros. And again, these zeros are going to be our x-intercepts. So think about what we did in the prior section and this section. In the prior section, we were looking at end behavior, minimum, maximum values, and we briefly talked about the x-intercepts. And now we're just expanding more on that. So although we're not going to graph this polynomial, think about how much we know about this polynomial so far. Well, it's third degree, so it has an odd degree. Leading coefficient is a positive 1. So odd degree, positive leading coefficient. Already I can see the end behavior. And not only do I have the end behavior, I now have all the x-intercepts as well. So now all I would need to do is just find a couple points in between those intercepts to get a better picture of what the graph would be. Again, we're not actually going to be graphing it right now. We're just looking at properties of polynomials, and in this section we're focusing on zeros and reviewing long division, introducing synthetic division. So let's continue on. In example 5, it says, for the polynomial a 0 is given. Find all other zeros. Okay, so it says that 4 is a 0 to this polynomial. So that means x minus 4 must be a factor by the factor theorem. So if I know that x minus 4 is a factor, then I know that p of x is equal to x minus 4 times something. So let's figure out what that something is by doing synthetic division. If I'm dividing by the x minus 4, I'm actually changing this to a positive 4 on the outside. And then what goes under the fraction bar is going to be the negative 1 in front of the x to the third, the positive 4 in front of the x squared, 7, and negative 28. Notice I'm not missing any terms here, so I don't need a 0 placeholder. Leave a space, bring down the first term negative 1, or the first number negative 1. Negative 1 times 4 is negative 4. So when I add, I get 0. 0 times 4 is 0. Add, I get 7. 7 times 4 is 28. Add, I get 0, which is exactly what I should have because I already knew that 4 was a 0, so I better get a remainder of 0. But why I did the synthetic division was for the negative 107, because that gives me that quotient. So this would be, the 7 is the constant, the 0 is the x term, and the negative 1 is the x squared. So that gives me a negative x squared, Plus 0x, I'm not even going to write it. I'm just going to put plus 7. What does this mean? Well, this means that p of x is equal to x minus 4, and then our quotient was negative x squared plus 7. And you can verify that by multiplying those together and seeing if you get our original p of x polynomial. So it says find all the other zeros. Well, let's look at the negative x squared plus 7. It must be true that if it is a 0, then negative x squared plus 7 has to equal 0. In other words, negative x squared is equal to negative 7. X squared is equal to 7. Square root both sides. Don't forget the plus minus. Square root of 7. Square root of 7 is a real number. And yes, we're allowed to get fractions and radicals and even decimals when we break these down into our zeros. So putting this all together, all the zeros would be the 4 that we were given, and then we have a positive square root of 7 and a negative square root of 7. And that's how we can use synthetic division to further factor our polynomial so that we can find all the zeros. And remember, we're finding all the real zeros. Okay, let's look at this in a different way, in example 6. In example 6, we're given a 0, and then what we're going to do is use that 0 to factor our polynomial into linear factors. So in the prior example, we were finding the zeros, and now we're going to use the zeros that we find to completely factor our polynomial into linear factors. So k equal to negative 5, that means that we're going to be dividing by x minus k, so minus a negative 5 would be a plus 5. So that would be a factor. I'm going to use synthetic division to break the polynomial down further. I'm going to take our negative 5 on the outside. Now notice I have x to the third, squared, x, and my constant. So again, I'm not missing any terms here. So I would put in the negative 6, negative 17. These are icky numbers. 63 and negative 10. Leave a space. Bring down my negative 6. Multiply by the negative 5 to get a positive 30. Add to get a positive 13. Multiply negative 5 times 13 is negative 65. Add to get a negative 2. Negative 5 times negative 2 is a positive 10. Add to get a 0, which I already knew because I was told that negative 5 was a 0. So if you do synthetic division or long division and you don't get a remainder of 0, double check your math. Translating the negative 6 to 13 and negative 2 becomes negative 6x to the x squared, sorry, plus 13x minus 2. All right, let's see where we're at. So our p of x, we already knew that the x plus 5 was a factor. And now we've used synthetic division to break it down into a negative 6x to the second plus 13x minus 2. Okay, does that factor? So if it factors, since it's quadratic, I know I need a 13, and I see that the 6 times 2 gives me 12, so I just need one more. So I'm thinking that it should be a 6x and a positive 2. So I'm thinking it's 6x times 2 gives me the plus 13 in the middle, but I need a negative, so I think it's a negative x. So 6x times negative x gives me the negative 6x squared. 6x times 2, this would probably be a plus 2, gives me the plus 12, and I need another, oh no, it would be a minus because of the negative x. Minus 1, does that work out? So 6x times negative x would give me a negative 6. Let me just do the math. Negative 6, and then the 6x plus 2 plus 12. And then a negative negative is a plus x, and then a minus 2. Yeah, it checks out. Okay, good. So this is how it factors. P of x is equal to x plus 5 times 6x minus 1 times negative x plus 2. So the question was to factor the polynomial into linear factors, and that's what we did. Each one of these 3 factors is a linear factor. This whole time we've been looking at the case where we're dividing by a binomial of the form x minus k, and that might not always be the case. So what if we are not dividing by the binomial x minus k? Well, in that case, let's just say that we're dividing by some random polynomial. We'll call it d of x. And we're calling it d of x because d stands for divisor, and that's what we're dividing by. Well, recall in the very beginning, we had this formula that said if you take a polynomial and you divide it by a binomial of the form x minus k, it's going to be equal to this polynomial, this quotient polynomial q of x, plus our remainder, which was a constant, over x minus k. So now if we are no longer dividing by x minus k, but instead just some generic d of x, then just substitute x minus k with d of x, and we get this generic formula where we have p of x, which is a polynomial, divided by any polynomial as long as the degree of d of x is less than p of x. And that's going to be equal to this quotient polynomial plus the remainder, but now the remainder might not be a constant because we're just dividing by any polynomial d of x. So the remainder over our d of x, which was our divisor. So again, r of x is our remainder, d of x, this is our divisor, and it's a remainder polynomial, a divisor polynomial. Q of x is a quotient polynomial. P of x is our dividend, but it's the dividend polynomial. So in the case that you're dividing and it's not x minus k, you're kind of stuck using long division. This is our last example, so we're going to review long division with any polynomial, not necessarily an x minus k binomial. In example 7, we want to divide this polynomial p of x, which is 3x to the 4th, minus 2x squared plus x minus 6. We want to divide by x squared plus 1. So notice it's not x plus 1, it's x squared plus 1. So I'm stuck doing long division. When I divide by x squared plus 1, I'm missing an x term, so I'm going to put in a 0 there. So x squared plus 0x plus 1. And then I'm going to divide, let's see if I have enough space, with the 3x to the fourth. I'm missing an x to the third, so it's going to be plus 0x to the third minus 2x squared plus x minus 6. Okay, so again, just look at the leading term on the divisor and on your dividend and ask yourself, what do I need to multiply the x squared by to get 3x to the fourth? And it should be 3x squared. So off to the side, if you need to, you would multiply the 3x squared times x squared plus 0x plus 1. And when you do that multiplication, you should get 3x to the fourth plus 0x to the third plus 3x squared. And that's what you would put underneath this 3x to the fourth. So it's going to be 3x to the fourth plus 0x to the third plus 3x squared, and we subtract down. When we subtract, we get, a lot of stuff cancels. The 3x to the fourth minus 3x to the fourth is 0. 0x to the third minus 0x to the third is 0. So then negative 2x squared minus a 3x squared would be a minus or negative, oops, I want blue, negative 5x squared. So when we bring down the next terms, the amount of terms we bring down has to match the amount of terms in our divisor d of x, which is 3. So we're going to bring down the plus x minus 6. We're going to look at the x squared in the divisor and ask ourselves, what do we have to multiply that by to get the negative 5x squared? And that would be a minus 5. So again, you can do that multiplication off to the side. You can take the minus 5 or negative 5 times the x squared plus 0x plus 1, which would give you the negative 5x squared plus 0x minus 5. And then we would subtract down. Negative 5x squared minus a negative, so plus 5x squared is 0. X minus 0x would be x, because this is a 1. So 1 minus 0 is 1x. Negative 6 minus a negative, so plus 5. Negative 6 plus 5 would be a minus 1. And then this is going to be our r of x. We're done with our division because notice that x minus 1 is a polynomial of smaller degree than our d of x. So once you get down to a polynomial that has a less degree than your d of x, your divisor, then you're done. So remember, it's always your q of x plus r of x over d of x, which means our solution is going to be 3x squared minus 5 plus remainder x minus 1 over the divisor. And now I'm going to leave off that 0 and just write x squared plus 1. So unfortunately, got to do the long division if you're not dividing by a binomial of the form x minus k. So that's it for this section.